Welcome to the solutions to the Thermodynamics Problem Set, problems number 33 through 35. Problem 33, a heat engine operates between two reservoirs at temperatures of 20 degrees and 300 degrees Celsius. What is the maximum efficiency possible for this heat engine? What you need to hear when they ask you what is the maximum efficiency possible for this heat engine is that they're asking you to calculate the Carnot efficiency. So setting up the equation for the Carnot efficiency, EC equals TH minus TC over TH. Keep in mind that your temperatures have to be in Kelvin. Make those conversions as appropriate. 573 minus 293 over 573. Do the calculation, 0.489. If you want to express it as a percentage, multiply by 100%, 48.9%. Pretty straightforward, easy problem for your first efficiency calculation. 34, a particular engine has a power output of 5 kilowatts and an efficiency of 25%. If the engine expels 800 joules of energy in each cycle, find A, the energy absorbed in each cycle, and B, the time required to complete each cycle. Alright, so going back to what we're given here, obviously we know our efficiency is 0.25. You have to express that as a decimal. And you're told that the engine expels 8,000 joules. And because of the wording, you know that that is the QC value. In A, they want the QH value, the energy absorbed. So we go ahead and we set up our efficiency equation, see what our options are here. And we see that we know E, we know QC, and we're looking for QH. So either one of these equations on the end will do. We go ahead and substitute 0.25 equals 1 minus 8,000 over QH. Solve the equation for QH. And we get 1.07 times 10 to the 4th joules. All right, next, we need to find the time required to complete each cycle. And you're getting used to this by now that time is tied to the power. So, let's see what we have to work with. Power is 5 times 10 to the 3rd joules per second, and power output is tied to work. So, it makes sense that the power that you're getting out of the heat engine is the rate at which the work is done. To calculate the work, we know that QH minus QC equals the work. And since we know the QH value, 1.07 times 10 to the 4th, and we know the QC value is 8,000, we can subtract and get a work value of 2,700 joules. Now we can simply use power equals work divided by time. Go ahead and substitute. 5,000 is your power, 2,700 is your work. 2,700 divided by 5,000 gives you the time, 0.54 seconds. Number 35. A power plant has been proposed that would make use of the temperature gradient in the ocean. The system is to operate between 20 degrees C, surface temperature of the water, and 5 degrees C, water temperature at a depth of about 1 kilometer. What is the maximum efficiency of such a system? If the useful power output of the plant is 75 megawatts, how much energy is absorbed per hour? And in view of your answer to part A, do you think such a system is worthwhile considering there is no charge for the fuel? All right, let's tackle A first. The maximum efficiency is the Carnot efficiency. So we set up our Carnot efficiency equation, make our substitutions, converting our temperatures to Kelvin. And we can see that we get an efficiency of 0.051, or as a percentage, 5.1%. Pretty low efficiency. Very low efficiency. More on that to come. B, if the useful power output, so again, the power is 75 megawatts, and you know that that's tied to the work done, how much energy is absorbed per hour? All right. Now, first thing we're going to do here is we're going to take your power output of 75 times 10 to the 6th. You have to use the 10 to the 6th for mega. Well, that would be 75 times 10 to the 6th joules per second. And what we're going to do is we're going to convert that to joules per hour. Doing that conversion, we get 2.7 times 10 to the 11th joules per hour. And what we understand is that is the rate at which the work is done. Now, if efficiency is work divided by heat absorbed, if we divide W by T and we also divide QH by T, we have not changed the efficiency equation. We're just including it as a rate of work versus a rate of energy absorbed. Note up here we have the rate of work. So, and they want, if we go back up here, they want they want how much energy is absorbed per hour. So they want us to solve for QH over T. We know the efficiency, we know the work done per hour. Go ahead and substitute, and we find QH over T to be 5.3 times 10 to the 12th joules per hour. Your answer to C is whether or not it's a good idea is really an opinion question, and that's a tough call at 5.1% efficiency. Though that efficiency is terrible, it's not costing you any money for fuel. So your only cost is going to be getting the operation set up. And if that could pay itself off, then this would be a worthwhile venture. But you have to weigh short-term expense versus long-term gain, and how long would it take for that power plant to pay itself off. So just some things to think about there. I look forward to hearing your answer on that tomorrow. All right, that'll do it for 33 through 35, and we will be working on the rest of the problems from this set of questions in class tomorrow.